Hello there, welcome to the time traveling debugger part 3. So this is going to continue off of the first two videos about the time traveling debugger proof of concept implementation that I have built over the holidays. This one I'm gonna focus on the internals or the how it works. Or just slightly lower level how it works. Last two videos I sort of gave you the high level how it works, but this is going to be a little bit lower level. So let's get right into it. Okay, so with the fun programming language, what you can do with the code is last time I showed you how to run scripts using or in funlang. So let's say if I wanted to run this vip.fun program, then I would vip.fun. I would use this run.js script to execute it like so, and it'll do it. However, you can also, in order to run a program, there's actually a few steps that happens. So the first step, so let me draw a diagram here. So you got your fun code. And so you're gonna write your fun code, and that's your vip.fun here. That's the fun code. The first step it goes through is the parser. Okay, which I actually regret drawing this as a rectangle now. I'm gonna go back and draw this guy as a circle because I want the artifacts to have a different shape than the machinery. So the machinery it is gonna be rectangles. So the fun code is gonna go through the parser, which will generate the AST, which stands for the abstract syntax tree. Which, if you haven't seen that, you'll get to see it very soon. And if you want a more detailed description about that, you can watch the video series I created about how to make a programming language. After you have an AST, you're gonna send that through actually to the checker first. We have a checker thing. We have a checker which basically checks if for impureness of functions in the case that you have written a fun, which is meant to be pure, among other things. But that's actually kind of inconsequential to what we're doing because it's gonna use the checker to tell you whether it's okay or not. So this is like gives you an okay, which is just a Boolean flag, and if it's not okay, it will give you some error messages. In the case that it is okay, then it'll take this AST and send it through another thing, and that's the thing we're gonna be talking about today. That is the code generator. I'll call that the code generator. What code is it generating? JavaScript. This code generator is gonna generate JavaScript, and then it's gonna generate a JavaScript program essentially based on the AST of the original fun code. And then once we have this JavaScript, we're just gonna send that guy to Node.js to execute this JavaScript code. And that's basically the plan. The main thing that had to change in order to support the time traveling debugger was the code generator. So that's the part we're gonna be focusing on. But each of these steps, I'm actually gonna skip the checker because that's not all that relevant in our discussion that we're gonna have today. So basically we're gonna manually sort of run the parser and then manually run the code generator and see what we get. Let's get to that. So how do we manually run the parser? Well, there's a parse.js. You just run that one instead of run.js, and it'll parse the fib.fun file and generate a fib.ast file. Let's look at that. So it looks like this. This is basically a semantic representation of what the code is. So it should make sense, as in this should be a accurate and meaningful representation of what this code is. So what does it say? It says the top level structure of the AST is an array because it's a number of different program statements, and each program statement has a type, and represented by an object, and you can sort of collapse these if you want. But basically, the first program statement is a proc definition, which that looks like so. That looks to be the case. It's a proc statement. So it's a proc definition statement whose name is an identifier. Name is yet another sort of node inside the AST, and its type is an identifier. The value is main, such the name main. And then the main, does it have any parameters? No, it does not. And then it has a body which contains a code block, and then the code block contains more statements. And in this one, there's 2 statements, so I should see 2 objects within the statements within the code blocks. So this is one, which is a var assignment to the variable result. And I should see another one, which is a co-expression to the fib function. Oh wait, no, this is still part of this var assignment. It's just the value part of the var assignment is the result of a call expression, which was this one, which we're calling the fib function with the argument a number literal of 8. Okay, so that all of this was the first statement, and then the second statement is a call expression to the print function. Well, it's a proc, not really a function, but you get the idea. So basically that is what the AST is. Again, if you want more detail about that, watch the other videos that I made. So then the next part, the more interesting part that I want to get into is the generator. How do you run the generator? You run the generate script, generate.js script. And you need to feed into it the AST file because, as we have seen, well, the generate step takes in the AST. So you do that, and we generate a fib.js because that's what the generate step does, generate some JavaScript code. Let's look at this JavaScript. Okay, so this is where the magic happens to allow the history collection and the snapshotting of every single state of the program. So the first thing is there's a history. Oh, by the way, I have put a $sign in front of a lot of these variables. These are global variables, and they're global to the entire program, but they're only used by this sort of back-in-time machinery. And the fact that they prefix with a $, character means that it's not possible for the function, the code itself, to have name collisions with them because the fun language does not allow $ characters in the variable names. So this kind of protects against that. So basically there's a history array which is going to contain every single snapshot. So you can think of it as at the beginning of the program, we have a state 1. And then the next time a snapshot is captured, which will happen if we call this save function. Then we have a state number 2. And every time this save happens, we'll have a new state stored where? Stored in the $history array. That's how it works. What is in the history? Well, the inside the history, what is a state? A state is an object that contains 2 entries, the line number. So this is just some number. Let's say 6. It has a stack something, which is an array of something. Let me write that out. A stack is an array of frames, which for now I'll write as ... and then it has a heap. Okay, so this guy is a snapshot or state. I will use those 2 terms somewhat interchangeably. So this guy is what is called a snapshot. And really the stack and the heap of a program sort of represents everything about the state of that program. And the line number is just telling you where in the program we were during that snapshot. So you can also see this stack variable and this $heap variable, and those are the representations of the current stack and the current heap. And they do update as the program executes. And we talked about in the last video, in part 2, we talked about the fact that within the heap we have this ID scheme. So like if there's an array in the heap, we actually give each object in the heap an array a unique ID, this unique ID, and this next heap ID is a counter variable that generates the unique ID as we go here. Okay. All right. So, but let's. So I got a whole bunch of this support code here with a bunch of functions, and also this save history function, which at the end of the program, it writes the history out to a file using the JSON R library that we briefly talked about last time. JSON R, yeah, JSON with refs, which we talked about, which is like JSON, but it adds the ability to have references in the file. So you can define an ID for an object or an array, and then later on reference it using this star syntax. So this and syntax defines the object that follows, and this star ID syntax refers to the thing that was defined before. Okay, so that's a trick that allows for structural sharing in this massive history object. Okay, so let's actually look at the code that sort of corresponds to the original source code, and that's going to be this main function and this fib function. You can already see it's quite a bit more complicated than the original source code. Let's do it side by side. Okay. Okay, so this PushFrame function and this PopFrame function, they happen every time a function is called, and the code for that is put immediately inside of the function definition. So, well, not immediately, after this variable. I'm not going to explain this for now. But basically, right inside of each function definition, we'll have a PushFrame and PopFrame. And you can also see in the fib function, we have a PushFrame and PopFrame. And what that does is essentially maintain add an entry to the stack frame, because if you remember, a stack frame is like a queue that when you call a function, let's say we just called main, it's gonna add an entry here, and then if inside the main function it calls fib, it's gonna add another frame here with a certain, I don't know, 5 or something, and then if fib calls itself, it's gonna add even more frames. So this PushFrame and PopFrame are the functions that maintain this creation and cleanup of these frames. So when it reaches the PopFrame, it's gonna get, or not that one, but I guess it would be this one. This one would be for the main function. Every time you pop frame, the frame gets destroyed. Every time you call PushFrame, you get a new frame. Okay, and we can take a quick look into the implementation of PushFrame and PopFrame. So a new frame is gonna contain the function name so that we know what function has been called to generate this frame, and then it's got the parameters that this function were called with, and as well as the initial variables, the initial local variables of the function. And then the stack is gonna be basically, this is using the spread operator to create a new version of the array that contains the previous content and the new frame. And the pop frame is just removing one from the end of the stack. So that's how the stack frame, the stacks of the stack frame get initiated. And then we have the variables. So whereas in the normal code, you just to do a variable assignment, you just have an expression and assign it to a variable. In the code that gets generated, we're gonna call the set variable function, pass in the variable name, and then we're gonna sort of execute the expression, which was here. We have an extra save here, which is to save the state of the program right after this function returns. So there's sort of like so really it's just so that the debugger will pause after this fib8 has been called and it returns. There's a pause to show that we're on this line between moving into the next line. Perhaps I should show that. So I'm gonna execute the debugger on this guy. So I'll show you that when you call the function fib8, so it's this. So the fact that the code pauses here after this fib8 returns is due to we have a save here to add another snapshot to the same line, because otherwise it would have skipped over to here. Maybe that's too low level, but so anytime you set a variable, you have to go through this $set variable function, and every time you call save, it will snapshot the current state, which again is just take the stack and the heap and stick it into the history array. And anytime you get a variable, you can't just reference the variable name. We're gonna call this $get variable function. So everything is very synthetic in a sense that we're not using real JavaScript variables. In order to get a variable, we have to look up the current stack, the top stack frame. So this gets the current stack, which is the last element of the stack array, and then accesses its variables and then looks up the variable name. That's how you get the value of a variable. And setting a variable is, you can imagine, grab the current stack frame, and then instead of making a modification to the frame, we can't do that because everything has to be done in an immutable way. So instead of that, we make a new frame with the change that we want, which we copy over the contents of the old frame. And because we're making a modification to the variables, we're going to copy over the old variables and then just make a change to the variable that we're wanting to change here. And then finally, we put back together the new version of the stack by first removing the current frame from the stack and then adding a new frame to it. Okay, and saving is simply taking a line number, creating a new snapshot. This object here, this inline object here, could have been called snapshot. And again, a snapshot contains a line, the stack, which we're just grabbing the current state of the stack, and the heap, which we're grabbing the current state of the heap there. So that's how all of this stuff works. And then there's this special return value variable, which is handy for just displaying to the developer the return value, what the return value of the function is going to be, which I have this specially named variable called retval for that. At a high level, you can simply think of this as the runtime of this program no longer uses the standard stack and standard heap on their own. Those facilities of JavaScript. Instead, it creates a synthetic stack for itself to use, so that the synthetic stack can be easily persisted into a file. Essentially, that's what's happening. And this synthetic stack is that guy. Here we have a bunch of built-in functions that are available in the fun language. And this heap allocate function is what generates a new ID for the heap. So it takes this next heap ID, which started at 1, but each time it does this, it'll add 1 to that, so that we'll get unique IDs. So this is how it generates an ID, and then again, it doesn't modify the heap, but it makes a new version of the heap, copies the old one over, and then adds this new entry here. That's how allocate heap works. And allocate heap used anytime program needs to create a new array or create a new dictionary. This actually doesn't happen here. Collect multiples. So when you create a new array, it would need to call allocate heap, and I can show it to you. So I'll need to parse the collect multiples program, and then I need to generate. And it needs to take in an AST. So let me so this is collect multiples, and this is collect multiples JS. Okay. All right, let's see what collect multiples JS looks like. So yeah, so when a new array is instantiated, we have to allocate heap in order to generate a new ID on the heap. Yep, and if we run the debugger, that's what gets us this ID 1 with an empty array at this point, and then the multiples variable points to the ID 1. And that happens because heap allocate actually returns the number 1. Heap allocate at the same time, it'll create a new entry in the heap. So basically, heap allocate is gonna make the heap look like this. And then at the same time, it'll return this 1 here. And that's what makes 1 go into the multiples variable as its value. Okay, so this is the code of the generator. This is sort of the runtime code, or the preamble, which has all these runtime support functions. which I have shown you. Get and set, I haven't talked about them, but basically get is to access an index within an array or to access a key in a dictionary. And set is the opposite of that, to set an index within an array or set a key in a dictionary. Oh, I didn't talk about the save history. Save history, well, I did a little bit actually. Save history takes in a file path, and it'll basically take the history array using the JSON R library to serialize it and then save it into that file. And that is always done at the end here, where we have this finally, and this file name has been sort of figured out by the generator. The generator just hard codes this file name so that after the program is finished, it'll take this history array, which has been accumulating the whole time, and serialize it and save it into this file. That's how that works. Okay, so generate code. How does it work? All the various places where it's either accessing variables or setting variables, we have to use these special functions. So var assignment has to generate code like this. And every line of code that needs to snapshot the state of the program, you just have to call this save function with the line number. And the line numbers are actually easily retrieved from the AST because all of the ASTs have attached with them the line numbers of the beginning of and the end of each node. So that's actually easy to get. So if we have statements like we have a proc main, let's say, and we have statement 1, statement 2, statement 3. Really, the general goal is to have stick a $save in front of each one of these, with some exceptions, but most of the time this is the case. We're gonna stick a save in front of each of these statements, and that allows us to snapshot the state of the program at every single step. Basically, all of the generated code have to be infiltrated, and this special machinery has to kick in. So I hope that gives you a good enough idea of how this stuff works. If you want to dig in deeper, you can check out the code. I've merged it into master of Funlang. So if you go to Funlang, check out the code, you should be able to run this code, run the debugger, etc. It's by no means production ready or even complete at this point, so you might encounter bugs, some of which I'm working to fix as we speak. Okay, so I hope you enjoyed that, and I hope to have another update for you about the work I'm doing with this programming language soon. See you then.